To add to your potential cognitive load, just a reminder that tonight things are due. A reminder that I've set up this course, and admittedly it's very experimental, not to have due dates at midnight the way you're used to, but 8 p.m. Why? Well, it turns out that there's decent evidence that circadian rhythms affect your school performance. So if you've looked at any of my research stuff, you'll see that in the last few years I've been collaborating a lot with a lab that researches circadian rhythms. And stuff like when you ask people in your age group to perform at 8 in the morning, they don't do so well, right? But also if you ask them to perform at 11 p.m., they don't do so well, okay? So it turns out there's reasonable evidence that you will do better at your cognitive skills when you are working, not oh my God early because of your age, but at my age, oh my God early is good, okay? But, you know, well before midnight, okay? That's why I'm changing the due dates, because I think our due dates probably encourage people to last minute stuff, and that probably means an awful lot of work is getting done at 11:16 p.m., right? So just as the deadlines come up, remind yourself it's 8 p.m. for this class, not 11:59. And hopefully that leads both to better work on your part and maybe you getting some chance to hang out with your friends in the evening instead of working right up until bed. I don't know. Okay? If anybody hates this or loves it, please leave me feedback. Okay? I would like to know if you like this or hate this, think I'm being some sort of nanny state dictator, or like if it's encouraging you to finally do things that you kind of wanted to do anyway. A reminder that not just assignment 1, but there's this syllabus quiz, which I don't care much about except for the fact that it's #financial aid, right? And if you are on financial aid and you don't fill out the #financial aid thing, then you might get an email that says that your financial aid is in danger. Right? If you remember, nowadays, because bureaucracy, we have to have you certify that, yes, indeed, you are actually in this class that you are receiving financial aid to be in. So that's got to happen. Any other questions, logistics-wise? No? Okay. Then let me blow you away with a super math slide. This is the big summary of everything we did last time in one slide. I want to not really go through it every detail, but I want to remind you of some details. So, the whole idea of regression is that we're trying to predict some y given some x. And this is the matrix notation, where we put the entire training set into that big X matrix. That X matrix is a design matrix, where rows on the X matrix are data points, and columns are variables. Okay? Now, critically, for this formulation of ordinary least squares, where we use just this kind of thing, right? Notice what's not here. There's no plus b, right? There's no separate bias term in this formulation. How can we get away with that? Well, we can get away with that if we put the bias term into the X matrix. If we have a column of 1s, then whatever other variables we need to have for each data point, right? Then that column of 1s acts as our bias term. It acts as the y-intercept on the line of regression. Does anybody have any questions on this reminder? Okay, so ordinary least squares is take the errors of each data point. So this is what is actually true. This is what we predict. And we want the sum of squared errors. So this is that difference between truth and reality. Multiply it by itself, that's the square. And the matrix algebra takes up the sum part, right? Because matrix transpose times itself is going to be a scalar. The thing is that we know that this guy here, that guy is a squared in W. W squared right here, baby. So because that's quadratic in W, we know that the shape is convex because quadratics are parabolas. So because we know it's quadratic, because we know it has one and only one minima, and that minima takes place where the tangent is horizontal, where the partial is equal to 0. Actually, I should write that better. I should write that as a gradient, where that gradient is 0. We can say, hey, I'm going to find that minimum by setting that gradient to 0, and then I can solve for everything, and I get that answer we came up with last time. Okay. That's it. Everything we learned in the last 50 minutes of course in one 4-minute slide. I'm sure it makes total sense. Yeah, what's the question?
Would x transpose times x just be equal to x squared, like in the function?
Yep. It's more to the point, it's all the elements of x squared and summed up. Right?
I'm just curious why the notation is different there with the gradient and loss function.
Sorry, you're talking about here?
Up one and to the right.
Here. Yeah, so this is when we do the first outer inner last stuff, and then we take the derivative of it. So one of the w's goes away. This term originally had a w in there before we took the derivative, and it was the w squared term. Okay? So this right here is the derivative, the gradient of w, right? So it's not a scalar because it's a gradient in the vector space. So it's actually a vector. And that's why this is not just a scalar because thing multiplied by itself. All good? As much as people have questions right now? Okay. Again, this is a summary to remind you of important things. Because what I want to do is I want to show you application-wise why this matrix notation is frickin' awesome. Because this matrix notation is one notation to rule them all. Okay? You can do all different kinds of regression using this one notation and applying it in each case. So base form, right? You got one x, you got one y. No matrices, no vectors. Just the kind of line of regression that you learned about in high school. Well, you can use this notation. There's no problems with that. Your output is, y is equal to a bias term plus a slope times x, right? We've seen this a gazillion times. So if you have a data set, right, here's a data set with pairs of x's and y's. So here's 1, 1. Here's 2, 1, 0.05, right? There's that data point. Here's 5, 4.1. That's that data point over there. Just one x, just one y. This is our training set. Well, that's a system of equations, right? The idea is that you take that regression line and you poke that through for every single data point, There's the first data point, 1, 1. There's that last data point, 4.1, comma 5, right? Sorry, 5, comma 4.1. I should say things the right way around. But you just take that same regression line equation, put all the data points in it, and you could solve for that system of equations because you have the right number of unknowns in there. Or you can put it in the matrix form. In the matrix form, here's the 1, comma 1, right? We have the output y at 1. We have the input x at 1. We have the bias column, right? B, the w sub 0, right? And 1 times w sub 0 is w sub 0. And 1 times w sub 1 is w sub 1. Right? And that equals 1. So 1 times w sub 0 is w sub 0. 3 times w sub 1 is 3w sub 1. And that equals 1.9. The entire data set on a 1x variable, 1y variable regression. Make sense? Okay. And you can solve this using the form we derived last time. Okay, what if instead of fitting a line, we wanted to fit a polynomial? Well, it turns out that you can do that exact same thing. In polynomial regression, what it looks like is we have just one x variable, but we transform the notation so that we have now multiple columns, multiple variables. We have the x variable itself, and we have that same x variable again squared. Okay? What do you mean, Jason? I don't get it. Okay, so we have the same data points as before. So let's take this one right over here. So the x value is 2. So when we do this one, that's this line. The system of equations is, wait, no, it's x3, not x2. Sorry, it's this one. Right? So this data point is 2, comma 1.05. Okay, so the equation system is right here. It's the bias term plus weight 1 times 2. 2 is our x variable. 2 squared is 4. W2 times 4. So what we're looking at here is, when we go into matrix land, here is our x coordinate. Here is our x coordinate squared. Right? So this is 2. 2 squared is 4. This one's x equals 3. 3 squared is 9. So the columns, the variables, are now going to be the bias, the x, and x squared. By doing that, we have explicitly put the square of x in as a term that we can regress on. So we're finding a parameter for the x squared term, which allows us to fit a polynomial to this line, to this data instead of a line. Yeah?
We went for like a triple.
Yeah.
We do x to the
You got it. However far you want to go.
Would it just be like w and x to the?
You got it. This is curve fitting. This is how you can fit a curve to data. And you're sitting there going, I thought ordinary least squares was a linear algorithm. How can you fit nonlinear things with a linear algorithm? It is indeed a linear algorithm. It's linear in the w's, not in the x's. As long as the matrix algebra is a linear combination of w's. We're all good. By explicitly squaring the x and making an x squared, or explicitly taking it to the nth power to make an x to the nth, we are doing the nonlinear part when we set up our x matrix. Okay? Any thoughts, worries? Okay, this is still the same algebra. So it's still the same answer. Yeah?
If you have a shape where it looks like one of the weights or unknown variables isn't just multiplied, it's like inside, for example, cosine wx, should you do something to y to convert, or should you use Taylor series, or should you do something else?
Okay, so you mean, you're talking about like having a sinusoid which has got repeating y's.
Yeah.
So you can, once again, you can put any nonlinear thing into an x column and try to linearly regress on it. Okay? That won't always give you the right answer, right? Because what you have here, like all of these kinds of shapes, they're monotonic, right? So there's no guarantee that something that has a repeating y can be done in this, I think. You should talk to a real mathematician. But you can certainly try by explicitly transforming and getting a column of cosine of x. And for at least trigonometric functions, I think this works. Because essentially this looks a lot like a Fourier transform, if you've ever done a Fourier transform. But I think it works. I can't give you a guarantee that it will always work with repeating y values. What if we have an absolute, sorry?
An exponential, like e to the power of an unknown
Yeah.
variable.
Monotonic, so absolutely, right? Yeah,
How
you
do
can.
you find the weight then, since the weight isn't just multiplied by x, or multiplied by it?
Well, it would be like if you made an explicit exponential of x column. Again, the nonlinear part has to be in the x's. Then it's a linear w, so it solves with OLS. Okay? But the concept here is you're transforming the x's, putting the nonlinearity explicitly into a new column of the x's so that you can assign a linear combination of the nonlinearities. Okay. And this is the form that we really started with, right? This is the idea that we first derived last time, which is that we have multiple x variables, x1 going this way, x2 going that way, and we're fitting we're fitting a y value, a single y value, which ends up being a plane instead of a line because we're in, multiple dimensions of x. So you fit a hyperplane, really. And that's explicitly the form of what we were doing yesterday, which is we have multiple x variables. We're regressing a y variable from those multiple x's. So again, this is all the same stuff. We plug in, in this case, we have 2 x variables for every single y variable. So it's a little different than the last 2 slides. But the idea is that we have 2 columns of completely independent x variables, and we're regressing that y. All of this is the same math. All of this gets the same ordinary least squares treatment. All of this has the same answer. The only difference really is in the setup of that design matrix X. So for the univariate case, we just get rid of all this stuff, right? We only just have a bias column and the x variable column. Okay? For polynomial regression, we have an x column and an x squared column up to x to the d, to use my notation that's there, the highest power we want to go to. And again, what we're doing here is we are making a nonlinear transformation of our data to allow for a nonlinear curve fit. Whatever nonlinear transformation you want to make is fine, whether it's cosines, exponentials, polynomials. If it's monotonic, it's going to work for sure. And if it's non-monotonic, I don't know any guarantees. Okay? And if we're doing multivariate, well, so in that case, this is x0, x1, x2, however many independent x variables there are. All the same math. Anybody freaking out? How can I help?
Is there a way to visualize multivariate functions beyond third dimension?
Generally speaking, there's no one way. People tend to use dimensionality reduction algorithms to display multiple dimensions, right, in just 2.5, so to speak, right, because we have fake 3D on this, right? But so mathematicians spend a lot of time thinking about how to show higher dimensionality and lower dimensionality. There's no one way. There's some cool books I can show you. Okay. So what if I tell you, this is all the same data set, right? The data set here is like, okay, we're measuring birth weight of baby on the y-axis, okay? So this is birth weight of a child. And on this axis here, this is a hormone level in the mom. And we're asking the question, is there a relationship between the hormone levels of the mom and the birth weight of the baby? Okay? So when we want to measure what we have, I should put the whole context here. This is an idea of model selection. These are 3 separate models here, right? Which one's the best model for the data we've observed? That's the big question, right? Is there a linear relationship? It's the same data points as when we put the polynomial. Which one of those 2 curves looks better, the straight line or the curved line? Right? How could we measure performance? One intuitive way is to use the loss function itself. Because we set up an algorithm that said that minimizing the sum of squared errors of the residuals is a good idea for making a good fit, the implicit understanding there is that's a good metric for measuring a good fit, right? We wouldn't be making that the best possible thing if it wasn't good for making good fits. So let's ask ourselves, what is our total training loss for the univariate case, for the polynomial case, and for the multivariate case where we're measuring not 1 hormone level, but 2 hormone levels in mom? So if we look at this, the univariate case is an order of magnitude bigger total loss than in the polynomial case, or the multivariate, which are close to each other. They're certainly not order of magnitude off. So let me ask you the question. Which is the best model to choose? Let's have a little quick discussion if anybody has some thoughts. If you were going to go out and say, hey, this is the relationship I think actually exists between hormone level and birth weight, what would you say? There's no wrong answers here. It's okay to spout opinions. Yeah? Can you say that louder? Sorry.
Yeah, sorry, what's the second variable that the multivariate is measuring?
So they're just two separate hormone levels. It doesn't matter for this case exactly what they are. Yeah.
I guess I'd probably go with polynomial because I think it's good for the data bed.
Okay. So to rebroadcast, I'm pretty sure you said polynomial fit because you think that's got the best look to it. Is there anything?
I just think that it's fitting the trend of the data better than where it is.
Okay.
Multivariate, because that's where we can get. I was going to say that's because where we can get the lowest loss rate.
Yep. So the multivariate case has the lowest total loss, which means it's quote unquote the best fit by this metric, right? Yeah.
I will also be multivariate because like it has a lot of data points, and the polynomial fit might be more correct than univariate fit, but like it might be overfitting.
Okay.
If you take a lot of data points, it might end up being univariate.
Okay. So there's two separate concepts here. You mentioned more data points. Do I understand you because I think you said you meant more variables? Because we have the same number of rows here. Okay, so it's more variables, right? Not more data points. But you mentioned overfitting, and that's also a completely interesting thing to mention, right? How do we know if we got, this is like whatever, like, 5 moms and babies. That's a pretty shit sample, right? So if we got another 10 or 15 or 50, would it still look like this quadratic-ish kind of function was the right thing, or would it actually turn out to be just linear with lots of noise, right? So that's overfitting. That's the question of overfitting. This is a more complex model, right? There's more degrees of freedom. This one has 2 degrees of freedom, the bias term and the slope. This one has 3 degrees of freedom. So does this one, right? So more degrees of freedom is a more complex model. It enables us to more easily overfit the shit out of noise. Okay? So overfitting is a valid concern here. More comments, questions?
Could you try and prevent overfitting by saying if one of the weights is like below a certain number, then round down to 0?
Okay. Can we prevent overfitting, for instance, by putting, I'm going to use a machine learning term here, a weight penalty on, right? If a weight value is kind of small, just scratch it out and replace it with a 0, because it's not really influential, and maybe that's just noise. Absolutely, guess what Friday's lecture is? Okay? But not yet. So I have a question for you. Do you think that it makes a difference that I said this was the loss on the training set? What if, oh, you can't even see this frickin' thing. What if that was the validation set loss instead of the training set loss? How would that change your answers? It's a question to ponder. I won't make you think about it out loud because I haven't really given you the background yet. Anybody who has an answer has got this answer from somewhere else. So at this point, what I'd like to do is to have a little bit of exploration. If you got your laptop open, it would be great if you would get this notebook live. Now, you can get this notebook live by, if you're here on the PDFs, clicking on these links. If you're not here on the PDFs, just go to github.com/cogs118a notebooks. Okay? Let me, come on, escape button, you should work. Let me get a notebook live here. So the link will take you to Colab. If you go to GitHub, cogs118a, do it that way. You could sync your, stuff to Data Hub if you want to do it on Data Hub. You can clone it down to your computer and use your Conda. We're doing O4 linear regression. But even if you're like right here, there's that Jupyter Colab button that's going to render in a minute whenever GitHub gets around to rendering. And clicking on that Colab will open up a live Colab. You'll probably, as soon as you get to Colab, you'll want to press this play button because Colab is going to take it like a minute to actually spin up an instance for you. So just click that first play button immediately. So here's what I want you to understand. What we're going to do is we're going to generate some cruddy data and fit regression models on it. Okay? That's what this exercise is about. We're kind of going to mimic what happened with the slides a second ago. But I want you to get used to scikit-learn for your first experience of actually using a machine learning library that we're going to use a lot. So if you've had 108 with me, we fit linear regression models using stats models in 108. Scikit will do linear regression. Let me tell you this straight up, right off the bat. If you are taking a model building understanding and your idea is to really understand the relationship between estriol hormone levels and birth weight, I think you should use stats models because it's a model building piece of software. Scikit is a machine learning piece of software. It cares about accurate predictions, not accurate models. If you don't change any defaults and you feed the same data set to stats models and scikit-learn, the weight values coming out are going to be different. Because scikit makes machine learning style assumptions. It applies a weight penalty by default because it's trying to prevent overfitting for you without telling you. Whereas a statistics package would never do that. It won't make assumptions. It'll assume that the modeler knows the assumptions the modeler is trying to make. Okay? So scikit is a piece of software that's got a machine learning outlook on life, and you should know that. Okay, but scikit is also super awesome, super powerful, and very, very uniform. Because scikit doesn't just do linear regressions, scikit will do just about any machine learning model that is out there, okay, with the same very uniform interface. And before we get into it, I want to give you the brief idea of how scikit works. Every single thing in scikit, like a linear regression here, is a class. And the class has certain methods. One of the methods it's got is .fit. So linear regression .fit will fit your training set. Then when you've got a test set, linear regression .predict will predict the thing on the new test set and get you out predictions. Okay? So every single linear regression thing has the same kinds of stuff in it. Whether it's a linear regression or a support vector machine or a neural network, it implements an interface that looks like .fit, .predict. And predict can only be called after you've already called fit, right? Otherwise, it doesn't make any sense. Okay, so let's go. What we're doing here, we're going to make some toy data. And in this case, the first one is going to be like this. So there is some true underlying generating function with the green line. And I drew a sample of 10 data points in blue that are built around that green line, but that green line plus random noise at each one of these data points. So the Y value started off as here, but then we added random noise to make that data point. Okay? So the green is truth. The blue dots are our training set. Okay. Let's fit a polynomial regression, right? 1 plus x squared up to x to the n. How many orders of polynomial? We don't know. We'll just have to see what we feel like. So if we're just going to fit a single x variable, right? This looks like, this is the x variable here. So that's 0 dot. This is the 0.1 dot. This is the 0.2 dot. This is the 0.3 dot, right? So here's all the x coordinates. Here's that bias column, right? Constant ones. Okay, how does this work? Polynomial features is a transformer, right? So it's a transformer that, sorry for the tooltips, I don't need that. You tell it, I want a first order polynomial. A first order polynomial is that, right? 1 plus x. And it implements the fit interface like all scikit estimators do. And when you give it xtrain, it fits the data set that we just saw here in blue dots. And then when you do transform, it transforms that data set into the polynomial you asked for. What if we want to do not first degree, but third order polynomial? Okay? So here's the x column, 0, 0.1, 0.2, 0.3. And here's that 0.111 squared is 0.012345, right? Here's that number to the cube, right? So we're fitting, in this case, 1 plus x squared plus x cubed. Okay? This is our design matrix. That same formulation that we saw back over here. Where's my good slide? This slide, right? This is the design matrix. So that features estimator, like all scikit things, implements a fit function, and then because it's not a machine learning system, it's a transformer, it uses transform to transform the data. So, if we want to, by hand, solve OLS using our known linear algebra we've solved for, we could do that, right? Features transform xtrain is going to give us the x matrix that we want. We can just take that xtrain, and you could write NumPy right there, right? You could write NumPy to do this, which maybe you've already had to do in A1, I forget. Did you have to in A1? In assignment 1? Maybe? Nobody? No? Okay, then it's probably in assignment 2. But I just want to point out that this is a code block where you could, right now, instead of listening to me, be figuring out how to use NumPy to implement that equation using xtrain. Why don't you give that a shot right now? So just a little thing to start you out. You will probably want import NumPy as NP. I don't know if I even put that up there earlier or not, but just in case. This will also be very helpful. numpy.linalg. Sorry, should write this. From numpy.linalg, import inv. inv is the matrix inverse operation. This -1 power, that's inv from numpy.linalg. And I'll give you a couple of other things to start you out. This is matrix multiplication operator. So it looks like matrix A at symbol B is matrix multiplication. And dot T is a matrix transpose. So looks like this. A dot T is the transpose of a NumPy matrix. I warned you there would be interactive content in this class. So maybe something like that. Oh, did I not? I got to run this one first, apparently. I didn't run that. Dummy. Okay. So I just kind of did it for you because time. So what we're finding here is that the bias term is about 1.3 when I ran it, at least, and the slope is about 2.79. The true generating function was not that far different, but not exact, right? I didn't get the exact true generating function. Why did I not get the exact true generating function? Why didn't I get the exact right answer that made the data? Yeah? Because it was noise, right? Because this random noise added to what had truly been this dot, right? We put a y deflection of noise onto that. So, all right. So I'm going to leave this stuff here, but if you're still feeling wonky in matrix algebra, it could be worth your while to just look at how the matrix multiplications go piece by piece. Like first looking at what x train is, and then look at x train dot transpose, and then xt times x, and then all of that inversed, and then all of, like piece by piece, just see how the linear algebra like ends up reducing all this down to a two rows, one column setup. Okay, it's just an exercise that might be helpful to you. All right. You're not going to do that ever again. I just showed you that because this is what's going on inside an ordinary least squares solver, and it's good for you to understand that. Because once you understand that, you understand what ordinary least squares really is. But when you actually do machine learning, what you're going to do is you're going to use scikit-learn, right? So if you go down here to there has to be an easier way, right? As I promised you, there is a uniform interface to every single machine learning algorithm in scikit. So we create our linear regression model, right? This act takes our linear regression class right here, and it instantiates it and makes an instance in memory of that class, a Python object. And that Python object is now called model, and it's ready for us to do something with. I am here to tell you that model.fit is the way you're going to fit the linear regression. just like with every Python machine learning algorithm in scikit. How could we find out what that should look like? If we put a question mark after anything in a Jupyter notebook, we will get contextual help, right? Model.fit, X matrix, Y vector, optional argument of weights to care more about particular samples than other samples. So sample weight is the kind of thing that's used like when you have a relatively rare thing in your data. So what if you're doing like political polling work and you just can't find enough people with the ethnicity of being black and Hispanic, right? You need to get an accurate picture of people's voting. You need to have enough samples of all the little subgroups to estimate voting, right? So if you only got 2 people who were both black and Hispanic, and you really needed 15 for your sample size, you can upweight those particular data samples and make them much more important. That's what a sample weight is. It says, I don't have enough cancer patients in my data. I don't have enough X, right? I need to give those few samples I really do have more importance in my training, okay? But at any rate, well, now we know how to do model.fit. So also in Colab, just the hover tooltip also works. Should work, maybe. There we go. There it does. At least in Colab, we don't get that in regular Jupyter notebooks. So yeah, you could probably fill this in for yourself right now, right? Have you already done it? Because I'm going to give you 30 seconds before I show you how to. You will always remember better if you do it yourself. So it looks like this: model fit x underscore train, comma y underscore train. So after the fit, we're going to get out, if we print like model.coefficients, we get those W vectors. And just in general, if you take a look at model, so scikit has this like visualization, like if you just take the train model and, oh, I guess it doesn't go beyond that for linear regression, but you can see all the elements of it the same way you would any other Python object. You can use dir, and it'll show you all the things hidden away inside model. So you might want to explore this, because every model that implements a supervised learning algorithm kind of looks the same. All right, one thing I want to highlight to you. This argument fit intercept equals false. Because we gave it that column of ones in the X, that's the bias term. You don't need scikit to fit a separate dot plus B. There's already a bias term in there because we set up that matrix that way. So if you didn't say fit intercept equals false, scikit would automatically put a plus B on this whole thing, and you'd end up with 2 bias terms, with each one of them having part of the y-intercept, okay? If you're just throwing in data and you never made this column of ones in it, you would definitely need fit intercept equal to true, right? Okay. So before you run out of here, I just want to set us up. Oh, come on. No? Oh, I didn't put the stuff down here. Ugh. Copy your fit and use a .predict down here for test set. Ah, Jason, we don't have enough time. Here. Let's do this. I'm going to do it super fast. Don't run away on me. So what do I need to call it? I need to call it y.predict. y_predict equals model. Man, can never type right when I need to. Equals model.predict x predict. Yeah. Okay. I think that's right. Let's see if that's right. Please work, please work, please do it right. Okay. We took the same blue dots and I fit a 0th order polynomial. That's just the bias term, no x. A 1st order polynomial, which is a line, a 3rd order polynomial, and a 9th order polynomial. Between now and next class period, I want you to think, which one of these is the best model? How would I know? Right? And we'll talk about it on Friday. Bye.
Hey. Basically, I've been on the COGS 108 waitlist for 3 quarters now, and I put in an easy request today because to be a full-time student, I haven't got enough to waitlist.